Okay, so hello and welcome everyone to the first interactive live session for the NPTEL course on computational fluid dynamics for incompressible flows. This particular course is being taught by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am a I'm a PhD scholar at IIT Madras, and I'll be the TA for this course. Every week, we will have sessions like this from 6 to 8 every evening, and we will be discussing a few problems which will particularly help you solve the assignments which are being given as a part of the course, as well as the final exam that you appear in. And the main goal of these questions is not to test your knowledge, but just to give you some practice. And more importantly, these questions should bring up, topics that you may have some doubts on. Maybe you went through the lectures and read some book on the same topic, but if you want to have a detailed discussion, we can have that here. Many of us will be joining every day, and we can have a very interactive talk on this. So, without any further ado, we will dive into today's session. But before that, one of our friends pointed out the importance of the Reynolds transport theorem. So, I'll start with a brief overview of what fluid mechanics is and what Reynolds transport theorem does, and how does computational fluid dynamics evolve out of basic fluid dynamics. So a very bird's eye level overview. The main things are very detailed, but we'll go through it very quickly. So it starts from basic mechanics, right? Mechanics, as we know, is the study of motion of matter. It could be anything, it could be solid, it could be fluid. For our current interest, will be uh, focused on fluids, which includes gases and liquids both. And so that brings us to the topic of fluid mechanics in general. And mechanics, again, has two different sides. It has kinematics and dynamics. So dynamics is kinematics describes the motion itself, not the cause of motion, and dynamics discusses the cause as well as effect of the cause of motion, which is basically force. So force is the cause and motion is the effect, and we study the relationships between them. So that's what covers fluid mechanics. So in basic fluid mechanics, we start from, you know, in basic fluid mechanics, we start with the Reynolds transport theorem, also known as RTT. So what Reynolds transport theorem does is it allows the connection between the second. So the all we know about motion starts and ends with Newton's laws. Okay, so Newton's laws are what governs all classical mechanics. Quantum mechanics would be a different thing, but right now we only know how to do classical mechanics. So Newton's law were developed for a control system or a mass. We know, right? All the equations of motion are related to some force being acted on a body of some mass m. Now, that does not talk about, but in fluids, identifying a particular mass is very difficult. So imagine this: I have a river flowing like this, and I'm trying to track, a blob of mass like this. I have drawn a very nice boundary here, but in an actual fluid mechanics scenario, uh, keeping that mass identified as it moves along, it deforms and does all sorts of weird things is very difficult. So here we have to move away from a idea of a control mass or CM to a control volume, where the scenario is like we have a camera and we are focusing our camera on a very specific frame and trying to look at it. So that is what a control volume is. So we will focus on a particular volume. So it's like fluid can, or any matter can come in, it can go out and do all sorts of things. So now, coming back to mechanics, all we know is Newton's law for a control mass. So what Reynolds transport theorem does, it is that it helps transform this Newton's law and allow us to apply Newton's law to a control volume. So from a control mass to a control volume, we can go. So that's what Reynolds transfer theorem does. And from Reynolds transfer theorem, we can, uh, you know, we will look into detail in one of the next slides what the uh, governing equation or the balance equation of any property is. It could be mass, it could be momentum, it could be something else. But all Reynolds transfer theorem does is that it allows us to apply Newton's law to fluids, which are deformable and stretchable and all that, and and which is moving along while deforming as well. So that's what Reynolds transfer theorem is, and so from Reynolds transfer theorem, we get something known as the Navier-Stokes equations, which again we will look into more detail later. Navier-Stokes equations is basically the governing equations of fluid motion, that if any fluid has to flow, it has to follow Navier-Stokes equations. So uh, as some of us pointed out that any derivation related to fluid mechanics can either start from Reynolds transfer theorem over here, which is the more fundamental thing to start from, or it could directly start from Navier-Stokes equations as well. This comes after some assumptions. So if we are starting from Navier-Stokes, we automatically make these assumptions and begin from there. So it's like a shortcut. We are not going through the uh, previous steps. We're starting from a well-known point that we know and understand quite a bit about, right? So we will assume here for this course that you have a fundamental understanding of fluid mechanics. If not, we will always go back and discuss those basics before we talk about computational fluid mechanics. Now, this is all very good. So Navier-Stokes is actually a partial differential equation. We will discuss types and ways to solve partial differential equations a little bit in week 2, I guess. And the thing is, partial differential equations, some of them can be solved by hand itself. It will be, very ugly equations, but they are solvable. But sometimes when the geometry becomes very complicated or the equations itself become a bit, so there are certain things called nonlinearities. There could be higher degrees of partial differential equations. Then solving by hand becomes very difficult and sometimes impossible at all. So in those scenarios, computational fluid mechanics come into the picture, where we use algorithms and computers to solve these PDEs for us, so that we can, get the solution of how fluid flows and how it can evolve, and you know, there will be very practical implications, like the way a fluid flows over a car actually determines the aerodynamics of it, which then again determines how much fuel would be required, which influences the economy of the car and so on. So there are very practical engineering and economic concerns which go down the line from our very fundamental physics and mathematical uh, studies. So that's the whole overview. Now, without any further ado, let's dive into today's session. We will look at some very basic questions. So the first question of today's session is asking us, what is CFD used for? And we have four options. So read these options very carefully and try to pick out the correct answer. And once you have picked out your favorite answer, you can either type in the chat box, or if you feel comfortable, you can unmute and answer as well, whichever way you feel comfortable. And if you have any doubt or any question along the way, please do not hesitate. Please just ask away. Yeah, right now I can see a hand raised. You can go ahead and unmute yourself, please.
The answer is studying fluid flow patterns.
Studying fluid flow patterns. Okay, so we have one response in favor of, sorry, we have one response in favor of studying fluid flow patterns. Let's see what others have to say. Someone has responded D, all of the above. Let's take a vote. Who says what? Okay, I'm getting more and more responses in favor of D. So we got 3 versus 1. Let's see what others have to say. There's no hurry. Take your time. Read through the question. So the question is, what is CFD or computational fluid dynamics used for? The options are option A, studying fluid flow patterns. Option B, designing new aircrafts. Option C, developing wind turbines. And option D, all of the above. Okay, so let's take a look at the answer. It's actually option D, all of the above. All of the above, A, B, and C, are all uh, typical use cases for CFD. Definitely, we can study fluid flow patterns, but uh, the use of CFD does not really stop there. CFD is a very widely utilized tool in many industries, be it the aerospace industry, be it the renewable energy industry, be it climate science, predicting the climate patterns over different regions of the earth, uh, can be solved using different CFD modalities. The working of engines, the working of many biological systems can be understood better using CFD. So there are just tons and tons of applications of that. So pertaining to this question, it should be option D, all of the above. So I hope that's clear. If you have any questions, you can ask. Otherwise, we will move along. We'll move on to question number 2 now, which is asking us what is the main difference between CFD and experimental fluid dynamics? So, computational fluid dynamics and experimental fluid mechanics. What's the difference between the two? Is it option A that CFD is simulation based while experimental fluid mechanics is physical equipment based? Option B, CFD is faster while experimental fluid mechanics is more accurate. Option C is CFD is more expensive while experimental fluid mechanics is cheaper. Option D, CFD is more reliable while experimental fluid mechanics is less reliable. Which one should it be? Okay, someone has responded B and D, B and D, then A, again A, again A once more. So we have a heavy inclination towards A this time. Let's take a look. Uh, okay, I think I got this wrong. Please don't be fooled by the coloring. It's option A that's correct and not option B, C, or D. So let's go through them one by one. CFD is simulation based, so that's what CFD is. It's a predictive tool which simulates reality. And experimental fluid mechanics is where you perform actual physical experiments using different equipments on how the fluid might flow given a certain situation. So you need a lot of physical equipments for that. So that's why option A is correct. Now let's go through why the other options are wrong. So CFD is faster while experimental fluid mechanics is more accurate. This in itself is wrong. CFD may not always be faster. Sometimes it takes weeks and months to simulate what in reality might be a few seconds, right? Depending on the complexity of the problem. Whereas uh, experimental fluid mechanics being more accurate, this part of the sentence is actually correct. Experiments are what reality is. Whatever we say, right, that seeing is believing. Whatever we see in reality is what is the most believable part rather than what a computer tells us. Then coming to option C, CFD is more expensive while experimental fluid mechanics is cheaper. Anyone has who has done some sort of experiments will tell you how expensive the diagnostic equipment for experimental fluid mechanics is. And CFD used to be very expensive, is still pretty expensive now, given that the computational power of our devices are increasing exponentially day by day and are getting cheaper as well. So that's why option C is wrong. Then option D says that CFD is more reliable, whereas experiments are less reliable. Once again, wrong. So basically, your CFD tool or CFD software is as good as the assumptions that you made while developing it, right? The theory that goes in is, however good your theory is, CFD is as good as that. It can't be better than that. Whereas experiments show us what the reality is. Often in CFD practice, you'll see that there is a very important need of validation of a CFD tool, whichever you're using. So you perform a simulation using a CFD, for which there are benchmark experimental cases, and you show that these two are matching. Then only people will start believing the results that you further generate using your CFD tool. So experiments are always most reliable, and CFD is as reliable as the results that you generate. If they match experiments, then it's fine and you're good to go. Otherwise, you have to do better. So option D again is wrong. So that's why all these three are wrong, and option A is correct. And I would like to apologize once again for the miscoloring of the options over here. A should have been in green and the other three in red. So we have some messages in the chat box. Let's go through them. So someone is asking what is the basic difference between CFD and fluid mechanics? And so the main thing is in so fluid mechanics is the broader study of the uh, study of fluid motion in general. So fluid mechanics deals with the motion of fluids, describing the motion, explaining the motion, why it happens, discussing the causes of that motion, as well as the implications of it. That's what fluid mechanics as a whole is. And computational fluid mechanics is a small uh, branch of fluid mechanics which deals with uh, finding out these questions related to fluid mechanics using a computer, using some algorithm. So fluid mechanics gives us a tons of PDEs, which are the or partial differential equations, which are the governing equations of fluid motions. These are known as governing equations. So any fluid that flows will follow these governing equations. Now, these governing equations are not always solvable by hand. In some cases, they are definitely. If you have taken a course in fluid mechanics, you will learn how to solve for, basic cases like a Couette flow, where you have, two plates, one of those plates moving, and you have some fluid in between, and you find out the velocity profile in between, right? I hope you're familiar to a case like this. Then there could be a pipe flow, which is like everywhere all around us. So we have a pipe like this, and we find that laminar flows usually take up a parabolic shape like this. So these solutions could be found by hand. Starting from the governing PDs, which are the Navier-Stokes equation, I can solve using my knowledge of solving differential equations what the final solution would be. But let's say instead of a pipe, I had a aerofoil like this of a weird shape, and I have some flow coming in, and that flow gets modified by the shape of this aerofoil, and it does all sorts of things. And I'm interested in what the lift force or the drag force due to this motion would be on this aerofoil. In that case, immediately I can't solve my differential equations. So I have to rely on some computational modality where there are different techniques which we will learn over this course, how to discretize those equations and how to then solve them. There are several algorithms, and those algorithms can luckily be implemented using a computer code, and that will give us the solutions of the fluid flow around it. So does that answer your question? Or if you have a follow-up question, you can definitely ask. This is the best platform which we have for our open discussion. Does that answer your question? Okay, I'll assume I've done a good job of explaining, sorry. And I'll keep moving. If you have more questions, please do not hesitate to ask. Let's now move over to question number three of today's session. So this question is now asking us what are the three main steps involved in solving a CFD problem? So there are different options given here. Read through them carefully and pick out your favorite solution. So option A is pre-processing, solving, and then post-processing. There is option B, modeling, simulation, and visualization. Option C says data collection, analysis, and reporting. And option D says design, manufacture, and testing. So we have a lot of responses in favor of option B. Three so far. Let's see what others have to say. We have a response in favor of option A. Three main steps involved in solving a CFD problem. These are the, you know, uh, widely used lingo in the world of CFD. There are three stages to solving any CFD problem. Okay, we have another response in favor of option C. Option D, anyone? Option D is feeling a bit left out. Okay, let's take a quick look at the solution. It's actually option A, pre-processing, solving, and post-processing. So this is the, sort of unofficial lingo which is used in the world of CFD, where pre-processing denotes anything and everything before you start performing a CFD calculation. So pre-processing involves developing, so let me write this here. So developing the geometry. We often use tools such as AutoCAD, Creo, SolidWorks to create a geometry. Then the next step would be meshing, which involves, breaking the geometry down into smaller pieces. So we will definitely learn more details on how to break them down and more details of it. But uh, just to give you a basic overview of CFD is that we take a big geometry, which is our actual geometry of interest, and then we break it down into small pieces, multiple small pieces, and we solve for the governing equations in those small pieces, and that gives us the main solution. So that's what, and apart from geometry and meshing, you have to set up the model as well. So model involves a bit more involved things like whether you're assuming a laminar flow or a turbulent flow will determine the actual equations which you're solving. So making a choice of that falls under pre-processing. Then apart from that, what do we have? Then setting the initial and boundary conditions. The initial and boundary conditions, setting them up. That's also a very important part in CFD. If you get your boundary conditions wrong, you will never get the correct solution. So setting this whole problem up is what comes under the purview of pre-processing. Then you actually go ahead and perform the calculation. That is what solving is. This is where uh, you press a button and wait for the computer to churn the data, churn some numbers, and throw up some solution. Then comes the last stage of CFD, which is post-processing, in which you take whatever numbers your algorithm gave you and you try to visualize it. That's one part of it, definitely, to visualize it. And that's not all. So let's say in one of the examples that I gave, that let's say you have an aerofoil like this and you have a flow past that aerofoil, just visualizing it is not enough. You may be interested in questions like what is the drag force on this? What is the lift force on this? Uh, Due to the shear force as well as the form drag. Right. So getting answers to questions like that also falls under post-processing. Then you might be uh, in a more detailed way, you might want to know what the uh, shear stress distribution on this aerofoil is, right? Where is shear force more? Where is it less? Then that would determine some more design aspects of it. You might want to tweak the design wherever the shear stress is increasing and uh, allowing more of those regions where the stress is less and so on. That all of these things depend on your actual objectives, but this also falls under post-processing. In case of heat transfer, you might want to know what the gradients of temperature are. That will give you how much heat you are losing at, sorry, at each and every point. So answering questions like that falls under post-processing. So this is the most generic uh, three main steps followed while solving a CFD problem. Pre-processing, which involves setting up the geometry mesh, models, conditions, etc. Solving, which is performing the actual calculations, and post-processing, where you visualize the flow fields as well as uh, different questions pertaining to it, like finding out the drag forces, the gradients, heat transfer, and all that. There could be a lot of things which falls under post-processing. Right. I hope that explains this whole, uh, what can I say, protocol of solving a CFD problem. So, uh, if you have any questions, please shoot them now. Okay, I have a question in the chat box. Solving methods. Which methods do we use? Discretization or numerical methods? So we will have to use both. And there are different options for them as well. Like discretization will have, different way. There are different ways of discretization. And numerical methods, which is the actual solving of the problem. There are multiple ways in which multiple numerical methods which can be implemented as well. So we will use both as well as, they come in different flavors. We can pick and choose which flavors we want depending upon our exact problems that we're dealing with. Any other questions? Okay, if not, we will move along. We'll move on to question number 4. See, you asked about discretization. We have a question about discretization. So the question is, which is not a way to discretize partial differential equations in CFD? The options are option A, finite volume method, option B, finite element method, option C, finite mass method, and option D, finite difference method. We have a very quick response in favor of option C. We have one response in favor of C, one in favor of D. One in favor of B. Two more in favor of option C. Let's see what others have to say. C once again. Option A, anyone? Okay, so let's take a look at the answer. It's option C. So finite mass method. So as I said, there are different ways to discretize partial differential equations, and options A, B, and D are different ways of discretizing it. So just to give you a brief, you know, overview of what these methods are. We won't get into detail right now. So over this course, we will learn finite difference method in great detail and a little bit of finite volume method. Finite element method can be used as well, but it's not so popular for fluid mechanics. It's more popular for solving solid mechanics problems. But anyway, fluid mechanics can also be solved using finite element method. It's not that it can't be used. It's just not popular. That's all. So just to give you a brief overview, finite volume method is something like this. So let's say this is your whole domain, right? Let's say these two are walls, and this is the inlet through which fluid comes in, and this is the outlet through which fluid goes out. Now, one way to discretize this geometry is to just break it up into smaller blocks like this, and then focus on one block. Now I'm zooming out on this block. So the thing is, every block within this whole uh, domain will follow the same governing equations that this whole block follows uh, in itself, right? So this is where Reynolds transport theorem comes into the play. So we will now say that every mass balance or every momentum balance equation is followed by every single block within this whole domain. So this block, which I've zoomed out from the middle, will follow mass balance laws. What does mass balance law tell? Mass balance law tells us that mass coming in and mass going out, they could be coming in and going out through all four faces because that's a like internal block. It's open on all four sides. So fluid could be coming in, going out, but the whole balance will be the same. So mass in, summation mass in, because it has four faces, right? Should be equal to summation mass out, because mass cannot be created or destroyed, something like that. Then similarly for momentum also, I can say that the sum of uh, momentum in minus sum of momentum out has to be equal to the sum of forces acting on this block. So there could be different forces which can increase or decrease momentum. It's not perfectly balanced like what mass is. Mass cannot be created or destroyed, but momentum can be created or destroyed by forces. But following Newton's law, forces would determine the integral momentum in and momentum out. So this is basically force into time. So this is not an accurate picture, but this is what finite volume method is in general. Then in finite element method, we discretize geometry as a you know uh, as interconnected masses, and we call them elements, and we assign certain weights to those elements, and then discretize the differential equation and try to solve it. Let's not get into more detail here. Even I do not know finite element method in much detail. And the other way, the finite difference method, which we will learn in great detail. So here again, we break up a bigger geometry into smaller blocks, right? So let's say if I started out with a block like this, I will break it up into points like this. So all these intersections are points that we care about. So this could be numbered, point I comma j. I goes from 0 to some m maybe, and j goes this way from 0 to n maybe. These are numbers which don't really matter, but that's just to identify a single point. And at each point, let's say we take this point, which is I, and I have a point on the left of it, which is I minus 1, and another one to the right of it, which is I plus 1. What finite difference method does is uh, it discretizes. The word discretize means that if I have a continuous function, it makes it discrete. So basically, instead of having uh, 1.5 2. These are what? Discrete numbers on a number line. So I'll draw a number line to be more accurate. So let's say I have x over here, y over here, 1, 1.5, 2. These are discrete numbers, right? Whereas I can have a continuous line like this as well, which follows, all real numbers in between 1 and 1.5, all real numbers between 1.5 and 2. So making a continuous function into discrete numbers is what discretization is in general. Now, what finite difference does is it breaks up gradients and things like that into these points, discrete points. So let's say if I'm interested in finding out dou u dou x at point I will simply say that it is nothing but u at I plus 1, which is over here, minus u at I minus 1, which is here, and divided by the distance between them. I'll call that 2 delta x. So let's say this much is delta x and this much is delta x as well. So it sort of dumbs it down. We lose some information, but we get an accurate number at a certain location. So there are many ways. What I did over here is a central difference. We will learn these schemes. There are forward difference schemes, backward difference schemes, and so on. But the main funda is this, that I have a continuous function like a gradient, and I'm breaking that up into discrete numbers, like one number minus another number divided by something. That's what finite difference is. I hope that gives you a broad overview of the techniques. We will discuss in detail later. We have a question in the chat box asking, do we consider the assumption of steady flow in finite volume method? We sometimes do, we sometimes don't. It depends once again on the problem. We can solve both steady as well as unsteady problems using finite volume method. So it's not an underlying assumption that we have to do that the flow is steady. It could be unsteady as well. Okay. Any questions on this? If not, let's roll along. We'll move on to question number 5, which is asking us which of these is not a regular structured grid. So, did you guys look at the lectures of week 1? I guess structured grid and unstructured grids were discussed. Okay, we have many responses in favor of option B, 3 of them. Let's see what others have to say. D once again. B, E. Okay. We have unanimous victory for D, which is triangular. We are getting more responses. Good, good. Okay, so the correct answer, as you all have guessed, is option D, correct? So, a regular structured grid. So, let's say, let's go through them one by one. Cartesian is this one, where we follow the standard Cartesian coordinate system of x, y, and z. For 2D, we will stick to x and y. And Cartesian grids look like this, basically rectangles. And we can have regular spacing and make it a structured grid. We can have irregular ones as well, but this is very easy to implement and think of. Similarly, cylindrical. So in cylindrical, our coordinate systems are, let's say, Z, R, and we have an azimuthal direction theta, let's say. So we can have a cylinder like this being its center line, and we can have, circles like this. So I'll draw ones over here. So we can have smaller circles gradually getting bigger. So these are concentric circles, which go all the way, by the way. So they span the entire z direction. And we can break this up in the phi direction as well. So they also go through. So we have circles like this. and straight lines like this. I drew a very bad picture, but I hope you get the idea. And we can have similar spherical coordinates as well, where we have one radial direction r and two angular directions. So it could be so let's say if this is a plane, which I'm calling x just for reference. So any elevation from that being theta and any rotation about it being phi. So this way is phi. So we can have you know uh, I'll try to do some justice to this, but please excuse my drawing skills. So let's say this is, sorry. So let's say this is one starting point, and I'll draw latitudes first, like this. So this is exactly like latitude and longitudes, which we learned in geography long back. And we will have lines like this, which are latitudes. And this can have concentric spheres bigger than this or smaller than this as well. So that's the R direction. And so this is what spherical is. Now triangular is a uh, triangular grids are very commonly used for making irregular geometry. So let's say I have a weird geometry like this, and I want to discretize it. Making it Cartesian, cylindrical, or spherical would be very difficult. But triangles allow us to smoothen out edges. So let's say I'll zoom out on this bit. Yeah. So this is a my drawing skills are amazing. So I'm zooming out this portion over here. So let's say I have a curve like this. I can approximate this by using a triangular grid. So let's say I take points like this and I make one triangle. I make another triangle. You can already see that, the I'm missing out this curvature. This is the true one, and this is what I'm assuming. And once again, you can see the difference, right? That there is an original curve, but I'm missing it by approximating a straight line. But if I take these points close enough, if I take very small triangles, which are very close, then that gives us a reasonable approximation of the curvature. And that's what matters, like getting an reasonably accurate solution. We won't get perfect solutions ever in CFD. Forget that. Uh, but it can help us getting these uh, for approximating curved surfaces using triangles. So triangles are very widely used, but here we let go of is a structured grid. We forget structure in it. What was available in spherical, cylindrical, and of course Cartesian. But it comes with the benefit of making these weird shapes work. I hope I could explain the whole thing clearly. If you have any questions, please go ahead. If not, let's move along. We'll move on to question number 6 now. Select the correct form of the general transport equation. So this actually comes from a differential form of the Reynolds transport theorem. Uh, and this is what forms the backbone of all the governing equations in fluids and solids also in general. Okay, so we have a response in favor of option A, option A again, option A. Okay, we have a heavy inclination towards A. So if you guys can excuse me, I'll be back in 5 minutes. You can take a break as well. So we have a very heavy inclination towards A, and that is the correct answer as well. Okay, so please excuse me. I have to be back in a few minutes. Yeah. Hi. So, sorry, guys, sorry for the delay. We are back, and we selected the correct form for the general transport equation, which is this first one. Where, so let's discuss this in a bit more detail. So, initially, we have what we call the temporal term, which is dou dou t of rho phi, plus we have the convective term, which is rho mu phi, and that is equal to the diffusive term, which is gradient of uh, nabla into, which is the gradient of gamma into the gradient of p, and we have a source term sp. So the main use of this equation is that if I replace p with anything, it could be anything as in any physical quantity which is conserved, uh, being the examples of this being mass, being momentum, being energy, or anything. I will end up in getting the balance laws for uh, that particular physical quantity, be it mass, momentum, energy, in a flowing system. So this actually comes from the Reynolds transport theorem, which is sort of like this. If I let's see if I can do this correctly. So Reynolds transport theorem tells us that the control mass on one hand. Question here. We derive many equations from these general transport equations, but why do we consider the dynamic viscosity of circulation in it? Because circulation and viscosity is totally no, gamma here is not circulation. Gamma over here is just a uh, gamma here is a proxy for a diffusion coefficient. So this basically tells us that if I have a field of phi, let's say phi over here, and I'm considering only one direction. Let's forget about 3D. Let's talk 1D. And if I have phi like this, if I have high phi over here and low phi over here, I will have a diffusion of phi, right? Away from high concentration to lower concentrations. That's what diffusion is. Now, how much diffusion will occur? That is proportional to this diffusion coefficient gamma. It's capital gamma, by the way. It's not circulation over here. It's just a diffusion coefficient. So for momentum, this will be viscosity. If it's energy, we will see that it becomes thermal diffusivity. If it's some species, so let's say if I have water and oil flowing together, or water and oil is a bad example. Let's say sugar, syrup, and water. So in that case, the concentration of sugar would also diffuse, right, from regions of high concentration to low concentration. In that case, the diffusion coefficient of sugar would replace this gamma. General transport equation comes from Reynolds transport theorem. So what Reynolds transport theorem tells us is that any so not dou dot t, so any change in a control mass would be equal to the change in a control volume. So change in control volume would be rho p into that volume integrated over the control volume plus a surface integral, the control surface. So I'll draw this. So if I have a control volume like this surface surrounding it is called the control surface. So and any small part of it may have a vector like this. It's the direction. So this part, let's say this is dA, the direction of it is along the n cap vector will be equal to rho phi into u at that location into dA. So dA vector is basically dA into this n cap. N cap is basically a direction vector. So this is what Reynolds transport theorem is. Now, uh, this term, as you can see, if we differentiate, gives us this, and this term, if we differentiate this, it gives us this. Not just direct differentiation would occur, you have to convert this. So a surface integral can be converted into a volume integral using Gauss divergence theorem. You must have learned this in maths. You can always go back and check. So Gauss divergence theorem helps us convert surface integrals into volume integrals. So this integral over here, the surface integral of rho phi u dot dA, we can convert this into a volume integral like this. Rho phi, sorry, not rho phi, we have to take now the divergence of it. The divergence of rho phi u, and instead of dA, it becomes dV now. So you can see how this term might emerge out of this term over here, right? And another thing, so the flow out of control surface is what this term tries to capture, and it only captures convective transfer. There could be diffusive transfer as well. So let's say something could be more over here and less concentration over here. In that case, it could diffuse out as well. And that diffusive flux is modeled by this term over here. And there could be generation of something in between. So uh, let's say energy or temperature is something that we're trying to model. And if something is burning, let's say you're trying to make a CFD simulation of a burning candle. In that case, wherever combustion occurs, a chemical reaction occurs and releases heat, right? So there is a source of heat in this problem. In that case, a source term also appears over here. In case of momentum, can you guess what a source term can be? Anyone? A source term, what can create momentum? Velocity is basically a proxy of momentum, that's fine, but what creates velocity? A force, exactly. And what kind of force do you imagine works within fluids? One, there could be many forces, but one popular thing, one very common thing that we discuss in fluid mechanics, what drives flows? So let's say if I have a pipe and I filled it up with water and I want to drive this water, what do I have to do? Pressure, exactly. So I have to create a pressure difference, and that pressure difference becomes then a source for momentum within this pipe. The water suddenly starts flowing as soon as I, uh, create a pressure difference across two ends of that pipe. So there could be similar sources for different things, except mass, because mass can't be created or destroyed. We learned this in eighth grade. So, uh, so to answer the original question, the general transport equation comes from Reynolds transport theorem, and it's basically a balance of what comes in and goes out and what gets generated. So it's you can apply this to the money in your bank account as well. So let's say uh, this is your bank account. I'll try to draw a bank very weirdly. So in case you have some money inside there and you want to find out at what rate your money is growing, that would be your temporal term, the rate of interest that you're getting. Not rate of interest, but rate at which your money is growing as a whole. And how can it grow? It can grow if more money comes in than goes out. So if your income is more than your expenditure, then this term will go up, right? So that those are fluxes coming in and going out. And what else can happen? You can generate interest based on the money that you already have. That is getting generated inside. That is the generation term or the source term. So fluxes in and out and generation, the balance of that will determine whether the whole thing is increasing or decreasing. That is what this temporal term signifies. I hope I could make this clear. Any questions? Okay. If not, we will move along. We'll now move on to question number 7, which is asking us what are the very high and very low Reynolds number approximations of the Navier-Stokes equations. Okay, we have option D. Let's see what others have to say. Option D again, option D again, option D again. Very good. So basically, we have went a bit ahead of ourselves, but let's try to write this down. So steady Navier-Stokes equations look like this. Dou u dou x plus, okay, I'll write in one coordinate system only. So 1D steady Navier-Stokes equations. They look like this. We have u dou x equal to um, mu dou to u dou x squared. If there is a pressure term, then I'll have dou p dou x as well, but let's forget this for now. So I have 1D steady state Navier-Stokes equations. And if I non-dimensionalize this now, this is another important concept. So let's say I write u as there's some scales associated with it. So let's say the velocity scale is u naught and the length scale is L. So I'll now non-dimensionalize u as u star equal to u over capital U naught, and I'll non-dimensionalize x or x star as x over L. If I now perform this non-dimensionalization, then what I'll get is u star dou u star dou x star equal to 1 over Reynolds number into dou to u star and dou x star squared. Hmm. Yeah, let's keep the temporal term as well. Let's not remove the steadiness of it. So let's say I have dou u dou t plus this. So in this case, I'll have dou u star dou t star as well, and there will be some time scale as well. Time scale can be L over u star. So these are scales for u, x, and time. Non-dimensionalization is a different concept. We will discuss this later. And if you I'll suggest you to go read through it. And if you face any problem, please come back and ask. We will have a more detailed discussion on it. For now, this is the non-dimensional version of the Navier-Stokes equation. And we are asking what are the very high and very low Reynolds number approximations of it. So let's say if Reynolds number, this one, is very high, it's a very high number, then what happens is that this whole term vanishes out. So let's go for RE high case first. When Reynolds number is very high, we can ignore this third term over here, and our equation simply becomes dou u dou t plus u dou u dou x equals to 0. This is one approximation. And Reynolds number very low, if Reynolds number is very low, then you can imagine that this term is very big and these two terms on the other side become very small. So now we can neglect them. So in this case, our equation simply becomes dou u dou x square equal to 0. These are all in 1D, by the way. And same arguments follow in 2D and 3D as well. So now this very high Reynolds number uh, approximation, this equation is known as Euler's equation. So Euler uh, in the 1600s, if I'm not wrong, 1600s or 1700s, came up with this equation, which is applicable for low viscous flows. So what happens in low viscous, in a scenario where viscosity is low and inertia is very high, you can ignore the uh, viscous stresses. The inertia overcomes it. So in that case, we can ignore the viscous term and take care of these two terms, and that should be uh, good enough. And that is what Euler's equation is. And this other one, Reynolds number very low, this is what is known as the Stokes equation, or flows or fluid flows where Reynolds number is very low. They are called Stokes flows as well. So this is common where the length scale is very short, very small. Means what? Let's say we are considering flow of bacteria. So this is the schematic of a bacteria where this is a bacteria and this is the tail attached to it is the flagella of the bacteria. And the lengths of these are in a few microns. Let's say it could be something like 200 microns or something like that. It's very, very small. So in that very small scale, the velocities are also very small. The velocities are in something like nanometers per second or maybe a bit larger, not more than that. Maybe in micrometers per second. That's all. That's the typical range of. So if you calculate the Reynolds number over there, the Reynolds number are like 10 power minus 3, 10 power minus 6, and so on. Very small numbers. So in that case, you can ignore the inertia at all. There is no inertia in the system. It's just it's like, so if you try to replicate this in a bigger length scale, it would be like moving honey or moving mobile or very viscous fluids. So there is no inertia. It's just the viscous force which determines the uh, deformation and flow of that fluid. So those kinds of flows are known as Stokes flows, which are low Reynolds number approximations. So basically what happens due to these approximations is that we don't have to worry about the full Navier-Stokes equations, which has more terms and they are more difficult to solve. And if we can smartly ignore a few terms which are less important, we get these simpler equations which are easy to solve as well, even for a case of even when you're applying CFD. So now coming back to this question, very high and very low Reynolds number approximation. So as I told over here, high should be Euler's and low should be Stokes. So option B should be the correct answer. Let's look at the correct solution. Yeah, so it's option B. This might be a bit involved, so I'll go back and I'll let you ask any questions that you may have. Any questions on this? So just on a side note, this Euler's equations, if we integrate them, we get the Bernoulli equation, which we learned in school and maybe in the basic fluid mechanics course uh, in bachelor's as well. So they are very important for solving pipe flows and things like that, for designing pipelines of a building or a chemical plant or things like that. Bernoulli's equation is a good approximation to start with. We can, of course, always go back and refine and write more, uh, so to say, sophisticated equations and solve them and all that. But Bernoulli's equation always gives you a good start, a good approximation. And that is one use case of the Euler's equation. On the other hand, the Stokes equations, okay, so before that, in Euler's equation as well, so let's say for inviscid flows, Euler's equations are once again a very good approximation. So for, let's say, very high velocity applications, let's say if I'm trying to design the wing of an aeroplane, uh, I have a very thin viscous region around the wing, and outside of that, there is a large bulk of flow which is technically inviscid because the gradients are very small. The velocity gradients are very small, so we can ignore the viscosity over there as well. So there again, Euler's equation might come handy. And the other spectrum of it, the Stokes equation. As I gave you the example of a bacteria, so recently there is a huge interest in microfluidics, right? You must have heard this term. It's a very trendy topic everywhere. Then the example of a bacteria, which is a case of biological fluid mechanics. So in this whole world, the equations they boil down to the Stokes equation as we saw, and they have another cool feature. They are linear. So the only non-linearity in a Navier-Stokes equation lies in the convective term, which is sort of the inertia of the fluid, right? So if we ignore that, our equations become linear, and turns out there are very simple techniques for solving linear equations. So that's what helps the scientists and engineers who are working on, microfluidic applications as well as, these very small uh, microbial flows and, flows within human cells and so on. There, this Stokes flow and Stokes equation becomes very important. So this was just to give you an idea of, what's going on around the world. Okay, so if you do not have any questions, we'll move along. We'll move on to question number 8 now, which is associated with certain equations and their forms. So, hoping that you are familiar with these equations, we have uh, the Fourier bio equation on as option A or equation A. We have the Poisson equation as option B. We have the Laplace equation as option C, and we have the diffusion equation as option D. These are all equations which govern very commonplace scenarios. Like the Fourier bio equation is very important for solving, heat transfer uh, from a blob, right? Uh, time unsteady heat transfer. Diffusion equation, you already know it governs diffusion of any quantity. And okay, and these are the options on the left, and we have another column on the right, which are the equations themselves. You have to, match the column as you must have done in school sometime. So as options, we have A1, B2, C3, D4. These are different combinations. First, figure this out, then try to find your combination from the options given here. So option A is A1, B2, C3, D4. Option B is A2, B4, C1, D3. Option C is A4, B2, C1, D3. And option D is A4, B1, C2, and D3. Okay, so we have a lot of responses in favor of option C. Right, in favor of option C. Take your time, try to do this carefully. So I'll jump into this. So let's start with the easiest one. The diffusion equation should be this one, right? Where there is just diffusion of temperature. Then we might want to take a look at, sorry, the time unsteady diffusion equation is this one. And Laplace equation is this one. Poisson equation is this one. And Fourier bio equation, in which we have the temporal term, the diffusion term, as well as a generation term, which is this one. So So I try to write this A4, B2, C1, and D3. Does that match with option C? 4, 2, 1, 3. Yeah, looks good. So let's take a look at the solution. It is actually option C. Good. Well done, everyone. Any questions on this? All right. If no questions, we move along. We move on to question number 9 now, which is asking us what are boundary conditions in CFD simulations? Is it option A, information about the fluid flow at the edges of the computational domain? Is it information about the fluid properties such as density, viscosity, and so on? Is it option C, information about fluid flow at the starting time? Or is it option D, all of the above? We already have one response in favor of option A. Let's see what others have to say. Option A again. Anyone else? What are boundary conditions? Okay, we have another option A. So yeah, let's take a look at the solution. It is actually option A, the information about the fluid flow at the edges of the computational domain. So boundary conditions are very important, as I said earlier, and I will repeat this multiple times over the next weeks. So uh, they are not only important for CFD, they are important for basic fluid mechanics where you're trying to find a analytical solution as well. But then again, there are different kinds of boundary conditions, right? So there could be a no slip boundary condition where u equal to 0. There could be a free slip boundary condition where, you know, whatever u you have, so that basically there will be no gradient. Dou u dou x would be 0, given this is x. Usually it's y, but I'll write x here. So free slip boundary condition. Then there could be a multiple kinds of boundary conditions, but they are important because they determine what the internal flow would be as well. Any questions on this? Okay, what are these, by the way? What is option C? Information about fluid flow at the starting time. What do we call this?
Initial boundary.
Exactly. Not initial boundary, initial conditions. These are also important in unsteady uh, simulations or temporal simulations where you start off with an initial condition and you observe its evolution over time. And in nonlinear dynamics, if you dig into it a little bit, nonlinear systems are very much dependent upon the initial conditions. You make the initial conditions a little different, the final state of the system will be drastically different. So these are again very important. Okay, I have a question. Any difference between general heat conduction equation and, sorry, any difference between general heat conduction equation and energy equation? I'm not sure what's the difference between the two. Uh, yeah, general heat conduction equation. So, conduction equation only holds true within solids. Once you have flow and convection, then you need to take care of the convection term, and that becomes a bit more complicated. And but also it becomes applicable to fluid flows where you have heat transfer along with flow, not just within a solid in a flowing fluid. Okay. All right. Let's move along. So this is our last question for today's session, which is asking us to match the following types of boundary conditions with their mathematical expression. So in the right-hand column, the math side, that's just the typical mathematical form of any equation, and these are the types of boundary conditions. So these are, some names given. If you remember them, that's much better because while describing something, we talk like that. So we say things like, okay, you can assume a Neumann boundary condition for this particular variable. So if you don't know what a Neumann boundary condition is, you might not get the uh, get what the other person is trying to convey. Okay, so we have Dirichlet, Neumann, Robin, and Cauchy boundary conditions on the left-hand side. And on the right-hand side, we have things like dou y dou x equal to f, the gradient being mentioned. Y equal to f, the exact value being mentioned. Option C, C1y plus C2 dou y dou x, a linear combination of the exact value and the gradient being equal to f. And option D, where we have two separate equations telling us the exact value as well as the gradient. So which one is what? We already have a lot of solutions. Man, you guys are fast. Okay, I have B, 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 and then D. So I have B, 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 and one in favor of D. Okay, so yeah, in Neumann boundary condition, a gradient is mentioned. So 2 should be A, and Dirichlet, you tell the exact value. So you say U equal to 5 meter per second, things like that. Then Cauchy boundary condition, you have um, the separate, you tell the gradient as well as the value separately. And in Robin boundary condition, you have a mixture. Robin boundary condition is also called a mixed boundary condition. You often see this in convection problems where, T as well as dou T dou X, they both come together and tell you uh, the exact heat being convected. Right. So, yeah. So the correct form should be 1B, 2A, 3C, 4D. B, A, C, D. Yeah. Option B, whoever said option B, you guys are correct. Yeah. Any questions on this? Okay, so if not, that ends our session here. Thank you all for participating so enthusiastically. We will continue with our discussions on this in every week. So, okay, there's another question that I have to ask. So, uh, one of you suggested that we shift this session a bit later. So, are any of you interested in that? So, let's say if we do not change, we will this will be our standard timing, 6 to 8 p.m. on Tuesdays, and we will have a total of 13 sessions. So you have got 12 weeks of lectures. We will have one session pertaining to each lecture, so each week of lecture. So this was pertaining to lectures of week one. Next week we will have questions pertaining to questions or lectures of week two, and in the end we will have one revision session. So 12 weeks of live sessions and 1 week of revision session in the end. That will be just before your final exam. So this is the basic format of it. I hope you all got it. I will bring some questions, we will discuss them. You will bring up doubts, we will discuss them as well. And in the end we will say good night and goodbye and meet again next week. So, okay, coming back. So, okay, please suggest some standard books for CFD. You can follow the book by Professor Dalal himself. I will. Okay. Uh, Hold on a second. I'll tell you the exact name of the book. Mm, okay, I can't find it now, but there is a book by Professor Amaresh Dalal and Gautam Biswas and one other author. I can't remember. I'll tell this to you next day. And other than that, for some international books, you can follow Versteeg and Malasekara. So Versteeg and Malashekara. My spellings might be wrong. Please check that, but I hope this is the one. And there is a book on finite volume method, a very good book by S.V. Patankar. He is the one who pioneered a lot of methods that we currently use in CFD. So you can read this book by Dr. Patankar. And what else? For this particular course, I think these three should be okay. The another one is Dalal, Biswas, and another author. I forgot the name. Sorry. I'll tell this to you next day. Or I can, share the, download link for the book as well. Okay, we have something else in this course. Any problem calculation will teach with any software or not for practice with? Yes. So in this course, we won't look at any software at all. This is not a uh, practical hands-on course. In this, you will learn the theory and the math behind CFD in detail. For learning practical CFD, there are some online courses available. You can check them. I don't think NPTEL offers any, but other online tools like Coursera and all that may have some. And the exact software companies themselves, they also offer tutorials. You can check those out. And for practice, uh, so I'll tell you the most popular CFD tools. The commercial tools will include ANSYS Fluent. This is hands down the most commonly used thing. Then we have another commercial software called ComSol. This is a multi-physics solver, but it can solve CFD with very good ease. For commercial softwares, you can learn these two. Commercial softwares are a bit easy to learn because they are more user friendly and you can use drop down commands and all that. And open source, OpenFOAM is the best one to learn. It's a bit difficult to learn early on. You will need a bit of coding knowledge and the exact way in which you have to set up open form simulation. There are many documentations and videos available online from which you can learn the basics of open form. But open form is a very versatile CFD tool because see this commercial tools you can use very well, but you can't really modify them. So let's say you want to propose a new technique of solving, or you're trying to solve a physics problem which has some very unique mathematics to it. So in open form, you can go and change the code itself. So of course, you have to learn a bit more, but it really allows you that freedom to absolutely go in and change the code. Commercial softwares won't allow you to do that. So these are the things that you can try out. And what I felt from personal experience, the best way to learn how to use CFD is to just pick a problem and try to solve it. So you learn the best while you're trying to solve a particular problem. I will learn CFD, the whole of CFD, or I will learn the whole of this particular software is not really possible because these are, vast topics of expertise which you gain over a long time. But just for getting started, take a very simple problem. Let's say you want to solve a pipe problem, flow through a pipe, and you use one software to do that. Then once you have the pipe solved, make it a little bit more complicated, add a bent pipe and so on, and you can add more and more complications and go forward. So yeah, that's all I have regarding this. Okay, Ramakrishna, hi back to you. So yeah, just to get to know each other, I'll repeat once again that I'm Debjit. I'm a PhD scholar at IIT Madras, and I'll be the TA for this course for this duration. And I'd like to get to know all of you better as well. So if you can, one by one, introduce yourself and tell us what you're currently doing and why are you trying to learn CFD, that'll be great. Hi, sir. I came from office. Can you share notes? So I won't be, yeah, I will be sharing these slides as well as these videos are getting recorded. They will be uploaded on YouTube as well. In the NPTEL page, in the NPTEL course page, you can go and find a link to that. As soon as this class ends, I will upload both of them, and NPTEL will share those links with you in 1 day or 2 days, maybe. You can go back and look at these slides along with the amazing scribblings which I made through them. And you can go back and look at the recording of these videos as well. So, yeah, so coming back to it, these will be our official timings. Now, if all of us agree, we can revise this timing to a bit of a later time. So, what do you all think? You can type in the chat box or you can, unmute and speak up as well. Does anyone else want to uh, postpone these sessions? Yeah, I have got very few responses. If unable to this live session, is there any problem in exam? No, no. Your attendance in these live sessions does not have any bearing on the exam marks. These are just for discussions and these are just for your learning sake. That's all. Six, 7:30 is okay. 6 p.m. is okay. 7:30 is okay. So I've got three people telling 7:30 is okay. So does anyone have any problem with 7:30? So once again, I'm asking for your opinion for shifting this, but I'm not 100% sure whether I'll be shift these or not because these are officially handled by NPTEL. I will put in a request if everyone agrees. And whether that request will be accepted by NPTEL or not is not really in my hand. So if we shift this to 7:30 to 9:30, does anyone have any problem? Let me know. Someone said no earlier with postponing. Do you have a problem? Hmm, 8 p.m. में मेरा mess है मेरा भी mess है bro को but yeah, this will be a problem since I'm a hosteler. I won't be able to get food if we shift these timings to 7:30 to 9:30. How about 7 to 9? Does that work? Okay, let's see. Let's have this same conversation next day as well. So as of now, I can see a few of you agree to 7 to 9 and some of you don't. So we have a split in the crowd. But yeah, I'll try to speak to NPTEL as well, whether shifting is possible or not in the first place. Let's have this conversation again next day. For now, we are meeting at 6 p.m. again next week. Okay. Whatever discussed, where can I get this? Yeah, these videos will be uploaded and this particular slide will be shared with you as well. Slide deck will be shared with you as well. From the NPTEL course page, you can go there and find a link in 1 or 2 days, not immediately. Okay. Yeah, Aniket is introducing himself. Hi, sir. I'm Aniket Bawade, currently pursuing BTech in Mechanical Engineering in Nagpur. Had a great time with the session. Thank you, Aniket. I had a great time with you as well. Others, if you're not feeling too shy, you can introduce yourselves as well. Rajiv, hi. Tushar is doing BTech in Aerospace. Yes, great. What about the others? Rajiv is doing MTech in Fluid Thermal at NIT Meghalaya. Nice. Conferences, yeah, there are many conferences. I don't know whether there's anything related to CFD or not. You'll have to check out in the website. I'm not sure. Ramakrishna is working as a vibration engineer at DRDO. Okay, nice. Pleasure to have you, sir. Agesh is from an engineering faculty from Kerala, got interest in CFD. Hi, welcome to this course. So we have some faculty members as well. So BTech guys, beware. Can you guide us in the core mechanical engineering jobs, career, etc.? I'm lost myself. I'm not sure I'm the right person to do that, but I will definitely try my best to guide you through this particular course on CFD for incompressible flows. But I'm sure we have faculty members and personnel from DRDO as well. You can connect with them. This could be a good platform to connect with each other and uh, get some advice regarding these things. Are you qualified the GATE exam? Yeah, I had to get admission to IIT for PhD, so it's sort of mandatory. I qualified GATE Mechanical back in 2020. Okay, so this was a great session. Let's keep this going. We will meet again on next week. And about this timing shift, nothing is fixed for now. I will let's have this conversation once again, and I'll definitely let you know. And these videos and slides will also be shared with you. And that's all. Good night. See you again next week. Bye bye.